Okay, welcome to lecture 4, and in this lecture I will be departing from I'll be taking an interlude from the slides, and we will focus in this lecture on Coulomb collisions. Since we talk a lot about Coulomb collisions in this course and how Coulomb collisions and the plasma parameter, okay, I thought I should go over the details a little bit. This thing. Sometimes it's called lambda. Sometimes you'll encounter this term, ln lambda. Okay, so let's see where this comes from. That's my primary brief, sorry, for this lecture, and let's see how it goes. One other reason I wanted to talk about Coulomb collisions is, of course, I mean, the obvious reason is that these are the primary kinds of collisions between charged particles, and they are, as such, a little different in nature, just because of the 1 over r squared nature of the force. They're a little different from collisions between between neutral particles that you might be a little more familiar with. Okay, so instead of preparing an entire entire set of slides, I thought I would go over this file, which is taken from a draft of Fundamentals of Plasma Physics by Callan that I got hold of from somewhere. I put this up on the materials folder, as you know. Right, so what we will do is we'll go through this, okay? We will read this, right? So yeah, so here is what the first thing I wanted to this entire section. You see, for neutral particles, collisions occur when neutral atoms or molecules come within about an atomic radius. You know, when they essentially bang into each other. Like that, okay. When they essentially bang into each other, and the electric field so the resultant collision is typically inelastic, and it causes the initial neutral to be scattered in an approximately random direction. And this is the so this is the cartoon that Callan likes to point out. What he has drawn here is these circles. These are the neutral particles, and they are inside a medium comprising charged particles. All right, you can think of these pluses as protons and the negatives as electrons, and these guys, these are neutral particles. So when neutral particles collide with each other, this you see, the trajectory is roughly a straight line trajectory, and the main thing to take home from this figure is that the deflections are relatively large, like so, big deflections. Okay, and I suppose this is a mistake here. This ought to have been a unfilled circle. Okay, and the typical distance between the neutral particle collisions is the collision mean free path for this kind of collision. All right. By contrast, Coulomb collisions in this kind of a plasma. Now, mind you, Coulomb collisions okay, I think I have that behind me. Yeah. So Coulomb collisions are also large angle collisions. Make no mistake about it. If you've got a positive charge sitting here and a negative charge zipping by, it will also it will not continue its straight line trajectory. It will, by virtue of the attraction, it will also be deflected. and it will be deflected by a relatively large angle. But the unique thing about a plasma is that, let me minimize this so that I'll find it easily the next time. The thing about a plasma in which there are lots and lots of these, positive and negative charges, there is Debye shielding, as we've discussed in a couple of earlier lectures. And because of this phenomenon of Debye shielding, the full potential of the positive charge is not really felt, and therefore the trajectory of a test charged particle, which is the electron in a partially ionized gas, exhibits continuous small angle deflections, like that. Small, it's moving along, and the deflections are relatively small, like that. Okay, and the collision length, or the mean free path, if you will, of a charged particle in a plasma is defined to be the average distance it moves in being deflected through 1 radian. Okay, here it's easy enough. It's the mean distance between each collision, and the collisions are very easy to define because the deflections are very, very pronounced. Here you see the deflections are not as pronounced, they're very gentle. So you just say you define an initial direction, and by whatever time or after whatever length, the deflection from this initial direction has exceeded 1 radian, you call that the mean free path. Okay, so this is the nature of Coulomb collisions in not necessarily only partially ionized gas, in an ionized gas. All right, now let's see how this comes about. Therefore, in the thing that we need to sort of keep in mind is that in a good plasma, right, what that means is that lambda, this plasma parameter, is much, much larger than 1. Small angle deflections predominate. Okay, and well, that's it really. Small angle deflections predominate, and so large angle deflections are rare. Okay, so this is a statement I've made, and we will find a way of justifying this also. But really, what are these deflections due to? The deflections are collisions. Deflections are due to Coulomb collisions, and so let's pay a little more attention to what these kinds of collisions are. Okay, right. So the geometry is, yeah. So that we will adopt the simplest kind of collision model. We first consider the momentum loss. Okay. And velocity diffusion. Velocity diffusion. Why should there be diffusion of velocity? Well, it must be if you paid very close attention to what I've been saying, you will immediately realize that it has to be so, because each collision is small angle in nature. So you started out with a velocity vector that looked like that, and then after one collision it looked like that, and so on and so forth. It's very much like a random walk, and you join these together, and that's kind of how it looks like somewhat like this. Okay, it's a bit of a random walk, and random walks and diffusions go hand in hand, right? So hence this emphasis on velocity diffusion. But let's keep that aside for the time being. Let's simply concentrate on momentum loss. Okay, and momentum loss of who? Of a test electron that's moving through a randomly distributed background of plasma ions that have charge Positive charges, essentially positive charges Zi times E, and they are stationary. They are massive, okay, much more massive, and so these collisions hardly do anything to them. They're just sitting there. All right, and right. And they say a little more, the background plasma electrons, which is they are the ones which ensure quasi-neutrality, but those are not the background plasma electrons. Are there simply there to ensure quasi-neutrality, and they will be neglected except insofar as they provide Debye shielding of the Coulomb potential. All right. However, the test electron, because this is the guy we will be paying attention to, the test electron can be thought of as just one particular electron in the plasma, and here is the the geometry. You've got, so we will just read the the caption, and so you've got the ion sitting here at yeah, so and the ion is moving this way, and the electron. We just said that the ions are stationary. So in the lab frame, the ion is indeed stationary, and the electron is whizzing past. It's right, and the ion is placed at the origin of the coordinate system. In the electron rest frame, it's sometimes little more convenient to shift to the frame where the electron is at rest and not whizzing past. So in the electron rest frame, the ion is moving in the negative z direction at speed v. In the lab frame, of course, the electron is moving in the positive z direction at speed v, and the ion is stationary, right? And here is one very important a very important quantity. It's called the impact parameter B. Okay, so what this impact parameter is this quantity, this guy. Okay, this. So and time t equals 0 refers to. So you see, the distance between the electron and the ion at this point is this. Right, and so the impact parameter is the distance of closest approach. So when it's here, when the ion is here, the distance between the ion and the electron is this, and so that is what we call time t equals 0. Okay, and just from the geometry, you've got b cosine phi, and so that's angle phi. So this would be b cosine phi, this would be b sine phi, and a few more. Yeah, so so the ion is seen to be moving like that in a straight line trajectory, and the equation of the straight line trajectory is this. Instantaneously, the electron is at the position x equals b, like that, plus vt. So this ex cosine phi plus ey sine phi is simply this guy, but you need to add the vt to it, and so with a z hat, right? And just from this, you can immediately write down the magnitude of x as this, where b is known as the impact parameter, and this is the geometrical meaning of the impact parameter, the distance of closest approach. So this thing, keep this in mind, the impact parameter, important thing to keep in mind. Okay, right. So yeah, it's a distance of closest approach, which by assumption, so the impact parameter is a distance of closest approach, which by assumption will occur at time t equals 0. And what are the forces at work? Well, the force, is simply the electrostatic attraction. Mind you, we are doing only electrostatics. Okay, we only consider the electrostatic attraction, attraction, repulsion, whatever. In this case, attraction. I want to emphasize that we are not doing electrodynamics here. The d over dt is negligible, which is why we Okay, only if there's sufficient. So please, which also means that electrostatics also means that the electric field can be can be described by a scalar potential like that. Okay, but please pay careful attention to when this electrostatic approximation can be justified. Okay. Anyhow, so the Coulomb potential, this guy is simply given by this. Note this is probably a nomenclature that you're more familiar with. So we're doing SI here. Callan. These are lab plasma physicists. Callan is a lab plasma physicist, and generally lab plasma physicists like to work in SI, whereas astrophysics people like to work in CGS. But you should be, equally comfortable with both, and you should figure out how to go back and forth. Just a side comment. Simply because you have the appearance of this 4 pi epsilon naught here. Okay, so the mod x appears in the denominator, and so that's that. It's a familiar, Coulomb potential. And what is the Coulomb force? The Coulomb force is just QE times E, and you get the E by taking the gradient of this guy, and the gradient taking the gradient of this essentially gives you a 1 over x squared behavior. So that's what it is. The x over x cubed, this gives you 1 over x squared behavior. This is simply there. You can equivalently write this as this, like that. It's the same thing. This and that are the same thing. Okay, right. What was I going to say? Okay, one thing to keep in mind. One important thing to keep in mind is the electron, in this case the ion, simply because of the electron we are talking about the electron rest mass, we're talking about the electron rest frame, sorry, but in the lab frame the electron is assumed to follow a straight line. Now this might, puzzle you a little bit. I thought it was a collision. There has to be deflection, right? I mean, without a deflection, what's a collision? We are considering the 0th order, where the deflection is quite small, and so this is the assumption. Okay, keeps things simple. All right. It's assumed to follow a straight line. The straight line trajectory of the electron in the lab frame. Okay, in the electron rest frame, well, the ion is following a straight line. Okay, the disturbance is very small. Okay, so please keep this very firmly in mind. Okay, so moving ahead, from having known the force, we calculate the momentum impulse, which is just m delta v, right? This is the impulse, as you know, and you get the impulse by integrating m dv dt from what you do is you do m dt dt, right, from very long before to very long after. In other words, let the ion go from very far away from the electron, where it practically has no influence on the electron, to close by, where it has the maximum influence, and then zips past and goes very far away on the other side. So you integrate all the way from here to here in order to get the impulse. This guy we are after. So this would give you this will give you m delta v. This is what we're interested in. Why, we will see in a minute.